first question is from tutorial 2, and it's question 4. And it says a typical person dislikes garbage. This means that more garbage is worse than less garbage. So this tells us that garbage is a bad. In other words, garbage gives disutility as we consume it. The less garbage we have, the more satisfied we are. The more garbage we have, the less satisfied we are. Part A then says, sketch several of a typical person's indifference curves between garbage and the composite good. Plot garbage on the horizontal axis. Okay, so how I would do this, now I'm trying to just open up my drawer. Okay, so how the indifference curves for garbage and the composite good will look here is garbage will be on the x-axis, the composite good y will be on the vertical axis, and the indifference curves are going to be upward sloping and convex. So I'm just going to draw a few of them, and I'm going to go through in a little bit of detail why it is that these types of indifference curves give this relationship between these two goods. Okay, so I'm labeling them I1, I2, and I3. And what that means is that I3 provides this consumer with a greater level of utility than does I2, and I2 provides a greater level of utility than does I3. Okay, so how can I figure out that that is what these indifference curves represent? That these indifference curves represent garbage as a bad and the composite good as a good. So garbage giving disutility and the composite good giving utility. So imagine that this person is currently consuming at this point on I2. So let's say for argument's sake, they're consuming G1 garbage and Y1 of the composite good. If they had to continue to consume the same amount of garbage, but more of the composite good, that should make them more satisfied because the composite good gives them positive utility. It doesn't make them worse off, it makes them better off. So moving from this point here on I2 vertically up would put this individual onto a higher indifference curve. Okay, so it makes sense that higher indifference curves represent greater utility. But then why do these curves have convex shapes? Okay, so the reason why the curve has a convex shape is because if this person was to consume just a little bit more garbage, that's going to make them less satisfied. That's going to give them disutility. So that's G2. In order to keep this person as satisfied as they were, so to keep them on the same indifference curve I2, that means that this additional garbage that makes them less satisfied, so it takes down their utility, that needs to be compensated for by a larger change in the consumption of the composite good. So that's why we have this increasing slope. So these indifference curves are increasing at an increasing rate, because in order to compensate for the loss of utility from consuming more garbage, this individual needs to then consume more of the composite good in order to keep them as satisfied as they were. Okay, so this type of example shows you very clearly how the shapes of indifference curves reveal somebody's preferences. So this is the picture for somebody who has a dislike for garbage, but likes the composite good. But what if we move to an example where we're dealing with an individual who loves garbage, but has absolutely no use for the composite good? So in this case, the individual in question is Oscar the Grouch on Sesame Street. So we're going to plot the same picture, but his indifference curves are going to look very different to the other individual. So again, garbage is on the x-axis, and the composite good is on the y-axis. And so Oscar the Grouch only gets utility from garbage. So we're just going to think again through this intuitively. So let's say Oscar consumes so much garbage and so much of the composite good. So he consumes G1 and Y1. If Oscar was to consume even a little bit more of the composite good Y2, what would happen to his overall utility level, his total utility? Well, because Y has absolutely no value for him, he sees no use for it, his utility would be exactly the same. So these 2 points would be on the same indifference curve. They would represent the same level of overall utility for Oscar. If he had even more of the composite good Y, same thing. Doesn't matter how much of the composite good he has, for this level of garbage consumption, he's going to have exactly the same level of utility. And so his indifference curves are going to be vertical lines. So let's, for argument's sake, this is I1. How would we then represent an indifference curve that gives Oscar greater utility than I1? So that would be an indifference curve like I2. So I2 gives Oscar greater total utility than I1 because this corresponds to a greater amount of garbage consumption. And Oscar likes garbage. So this picture here shows us indifference curves that reveal preferences that are dependent only on, or the utility is dependent only on the good that is on the x-axis, but it is not dependent on the good at all on the y-axis. So this is how we can end up with a whole range of differently shaped indifference curves. Typically, our indifference curves look like this. They're downward sloping and convex. And this is because of those axioms that give us well-behaved preferences or well-behaved utility functions. And that means there's monotonicity, there's transitivity, there's continuity, and diminishing marginal rate of substitution. So that gives us this shape indifference curve. But if we take away some of those axioms, and more specifically, the more is better one, the monotonicity one, then we get these different shaped indifference curves. Okay, so I see a question in the chat. If Oscar had no use for garbage and loves the composite good, would it be horizontal? Absolutely, exactly. So an individual who gets neither utility nor disutility from garbage and only got utility from the composite good, they would have perfectly horizontal indifference curves. During the semester, we also saw an example where we have an indifference curve that has a y-intercept. It's not perfectly horizontal, but it has a very slight slope. That shows preferences where the individual gets most of their utility from consuming the product, the good that is on the y-axis. So the shape of the indifference curve tells us about this person's preferences. So what we could see, for example, with this indifference curve here is that, and I think the example that we looked at in the semester was this is shelter on the x-axis and this is food on the y-axis. What we're saying here is that this consumer would be able to get some positive utility by consuming only food. So if they were consuming at that y-intercept there, they would be consuming absolutely no shelter, but they would be consuming food and they would be able to get some positive utility from that. If they had no shelter and less food than that, that would mean they're on a lower indifference curve, because having no shelter and now even less food would make you less satisfied. But this kind of indifference curve map shows you that it is possible to get some utility through consuming only one good. Whereas indifference curves that look like this, which are asymptotic to the axes, so they never touch the axes, either the x or the y-axis, those type of indifference curves tell us that this person's utility is dependent on both the two goods. So this individual would need to consume some combination of both of these goods in order to get any kind of utility. It would be impossible for that consumer to get positive utility if they consume nothing of the one good. Okay, so this is just a good question to see how indifference curves reveal a consumer's preferences. Okay. The next question I'm going to look at is a really, really simple one. But I think sometimes, with these true and false questions, just like yesterday, I think you need to think through, is this true all of the time? Is the statement saying something that there is no example where it isn't true? So what you're trying to see is this statement necessarily true all of the time? So the question says, if you know the slope of the budget constraint for two goods, you know the prices of the two goods. So for example, what this is stating is that, let's say a budget constraint has the slope -0.5. And we know that the slope of the budget constraint comes from taking the relative price of the product that is plotted on the x-axis. Now, looking at this formula here, what we can see then is that this value of -0.5 only tells us about the relative sizes of those two prices, but in no way can it necessarily reveal the exact values of those two prices. So all I can tell from the slope is that Y is twice as expensive in money terms, in monetary terms, as X. So for example, the price of Y could be 50 Rand. That would then tell me that the price of X is 25 Rand. So in order to be able to extract the prices from the slope of the budget constraints, we would need further information. The size of the slope doesn't give us enough to be able to extract the individual prices. Okay, so when you're doing true and false questions, always think in that way. Always think, is this necessarily true all of the time? Is there any case or example or way in which I can reason that this statement cannot possibly be true? Okay, so that's the reason I wanted to show you this question, just to again remind you how to approach true and false questions. Is everybody happy with those first two questions? Very simple theory of indifference curves and budget constraints, but it helps to just ease into the theory before we get to some slightly trickier questions. Okay, so I'm going to move on to question 4 from tutorial 3. So this question used the Lagrangian method to solve it, but you don't need to use the Lagrangian in order to solve this kind of question. So that's why I've pulled this question out of the tutorial. The whole point of the Lagrangian is to give us first order conditions that allow us to find optimal consumption points for an individual consumer. Those first order conditions, there were 3 of them. So you take the Lagrangian, you take the partial derivative with respect to y, with respect to x, and then with respect to lambda. And those then give us 2 results. And those 2 results that we get is that to optimize a consumer's MUX over price of X must be equal to the MUY over the price of Y. Okay, I'm going to try and draw this a bit better. Yeah, just rub that out. Ugh, no. No idea why the eraser is not working now. There we go. Okay, so the MUX of the price of X must be equal to the MUY over the price of Y. Ugh. My pen is not cooperating. Okay, so that's the one thing. The other thing is that the consumer must spend all of their income. So their income must be equal to the price of X times X plus the price of Y times Y. Okay, so these are the two things that must be true. The other way that I can represent this over here, so that representation that I've just outlined, that is Gauss's second law. I can also represent that as MUX. Ugh. I think this is also lagging because of the connection. MUX over MUY. This is where you find out that Max and Microsoft just do not like each other. So MUX over MUY is going to be equal to the price of X over the price of Y. So those are the two ways that I can represent that tangency. So this MUX over MUY, that's my marginal rate of substitution. So that is the rate at which the consumer is willing to trade the two goods. And then the price X over the price Y is the opportunity cost of X, the relative prices of these two goods. So that represents the rate at which the market wants the consumer to trade these two goods, or the rate at which they have to trade these two goods in the market. Okay, so these are the things that need to be satisfied for a consumer to be consuming at their optimal point. So we're going to use these conditions with the information provided in the question in order to solve for how much of each good should Xuma buy. So Xuma has $118 of weekly income, and they spend this income on X and Y. The utility function is given by U of X and Y is XY plus X. The price of X is $10 and the price of Y is $2. Okay, so this is all the information that we need in order to solve this particular problem. Okay, so the first thing we're going to do is we are going to get the MUX and the MUY. So how do I find the MUX using this question? I find the MUX is going to be the partial derivative of the utility function with respect to X. So if I take the partial derivative of xy plus x with respect to X, I'm going to get Y. And then the partial derivative of X with respect to X is going to be 1. So taking the partial derivative of xy plus x with respect to X gives me Y plus 1. Okay. Then if I want to find the marginal utility of Y, I'm going to also do the same thing. I'm going to take the partial derivative of the utility function with respect to Y. And so if I take the partial derivative of xy plus x with respect to Y, X now becomes a constant. So the partial derivative of xy with respect to Y is simply going to be X. And the partial derivative of X with respect to Y is going to be 0 because X is a constant. So now I have my two marginal utilities. I've got the marginal utility of X is given by Y plus 1, and the marginal utility of Y is given by X. So what we can now say is that Y plus 1 over X is equal to 10 over 2. So that is basically me saying that MUX over MUY is equal to the price of X over the price of Y. I'm now going to simplify this out, and I'm going to say that Y plus 1 over X is equal to 5. So Y plus 1 is equal to 5X. And so Y is equal to 5X minus 1. So now we know that whatever Y is at the consumer equilibrium, the consumer must be consuming exactly 5 times however much X they're consuming minus 1, and that will be equivalent to the amount of Y that they then will consume. Okay, so what we're going to do now with this here is we're going to sub it into our budget constraints. So this is the one condition for the consumer equilibrium, MUX over MUY equals price X over price Y. The other condition is that the consumer must spend everything that they have in income to spend. So their income must be equal to the price of X times X plus the price of Y times Y. So I'm going to sub in my income and price values, and that's going to be 118 is equal to 10X plus 2Y. So that's the consumer's budget constraints. And now I'm going to sub Y with this that I've just calculated. Y is going to be 5X minus 1. So 118 is going to be 10X plus 2 times 5X minus 1. And so I'm going to have 118 is equal to 10X plus, and I'll multiply 2 into the brackets, 10X minus 2. Now I'm just going to collect all of the constants together and the 2 X's together. So if I take the minus 2 to the other side, I'm going to get 120. So 120 equals 20X. And that means that X at the consumer's best point is going to be 6. So I've solved for the consumption choice of X. But then how do I get my value of Y? I sub that 6 back into that function Y equals 5X minus 1. So if X is 6 at the consumer's equilibrium, then Y is going to be 5 times 6 minus 1, which is going to be 29. So what I've done is I've solved for the consumer's best optimal choice of X and Y, and they're going to end up consuming 6X and 29Y in equilibrium. Okay. Does that make sense to everybody? So you could get a multiple choice question where you get given this information, and then you might be given different combinations of X and Y, and you need to solve and see which one is the correct bundle. Okay, but is this question fine for everybody? Or is there anything that you'd like me to go over or to repeat? Okay, I see a thumbs up. I'll just see if anyone wants to mention anything in the chats. Otherwise, we can move on to another question. And I think the next question that I wanted to do was tutorial. So it was tutorial for question 2. Okay, so tutorial 4 question 2 is actually a very similar question, but what it does as well is it brings in a price effect and in a Hicksian decomposition. So yesterday I did a question where I showed you the Hicksian decomposition using a graph, but as we know, with everything in economics, whatever you can do with a graph, you can also do with pure math. So I'm going to go through this question because it helps you to see how the mathematical functions and the graph correspond to each other. So in tutorial 4 question 2, the question says Louise has the utility function uxy is equal to xy. So that's the utility function. Her income is 40. The price of product Y is 2, and the price of good X is 4. And then the question starts by asking, what is her initial best affordable bundle given the preferences, income, and the prices of these two goods? So we're basically just going to repeat what we just did. We need to find MUX, and we need to find MUY. And once we find both of those, we're going to equate the ratio of those two to the price of X over the price of Y. Okay, so MUX we get by taking the partial derivative of this utility function with respect to X. So in that case, Y becomes a constant. So if I take the first derivative of XY, I'm going to get Y. Okay, Y is a constant just like a number, so 2. So imagine this was just 2x. If you took the first derivative of 2x with respect to x, you would get 2. So you're just left with the constant that is applied to that variable. So the marginal utility of x is y, and the marginal utility of y, same logic. If I take the first derivative of xy with respect to y, and x is now a constant, it's going to be x. So those are my marginal utilities. And I'm going to equate that to price X, which is 4, divided by price Y, which is 2. So that means that Y is going to be 2X. So 4 divided by 2 gives me 2, and I take X to that side, so I get Y equals 2X. So that is my equilibrium solution for these two goods. Whatever amounts of X I consume, I'm going to consume twice as much Y. Okay. Then I need to sub this into my budget constraint. So my budget constraint is going to be 40 is equal to 4 times X. So the price of X times X plus 2 times Y, the price of Y times Y. So if I sub in Y is equal to 2X, what I get is that 40 is equal to 8x, 4x plus 4x. And that means that x is 5. And if x is 5, it must then mean that y is 10, because I'm going to consume twice as much x in the form of y. So this is the best affordable bundle of Louise, initially for her given income preferences and the prices of X and Y. The next part of the question then asks, what is her total utility that she gets from her best affordable bundle? So now what I do is I take these values of 5 and 10, and I substitute those into the utility function. So her total utility for 5x and 10y is simply going to be x times y, which is 5 times 10, which is 50. So her total utility at her best affordable point is 50 utils. Everybody happy with that? Okay, so I'm going to move on to the next part of the question. So the price of X now increases to 5. So the price of X used to be 4, but now it rises to 5. Okay, how is this going to affect her best affordable bundle? So we're going to do exactly the same math, but making sure to plug in our new value of the price of X. Okay, so if we try to find her new best affordable point, what we're going to have is that her MUX over MUY must still be price X over price Y, because that always has to be the case at her best affordable bundle. Her utility function is still the same, which means MUX is still Y and MUY is still X. But now her price of X is 5 and her price of Y is 2. So that means that Y is now going to be 2.5x. So given the new relative price, she is now going to be at her best affordable point when she's consuming 2.5 times more Y as she is consuming X. So again, we're going to sub this into a budget constraint, but her budget constraint has also changed. Her budget constraint is now going to be 40 equals 5x plus 2y. So the price of X is now different. So 40 is now going to be 5x plus 2 times 2.5x. And so 40 is now going to be 10x, 5x plus 5x. And so that means that she will now consume 4 units of X at her best affordable points. And if we sub those 4 units of X into Y equals 2.5x, it means that she will consume still 10 units of Y at her best affordable bundle. So the result of this price increase in X is she consumes less X. She used to consume 5, now she only consumes 4, but she doesn't change her consumption of Y. Her consumption of Y is still 10. So the next part of the question then asks, what is the total effect of the price change on her consumption of X and Y? So the total effect on X is minus 1x. She consumes 1 less X than she previously did. The total effect on Y is 0. Absolutely no effect on her consumption of Y as a result of this price change in X. Okay, so that's the total effect. But the total effect of any price change can be decomposed into 2 parts. It can be decomposed into a substitution effect and an income effect. So what we're going to do now is we're going to use math to find the substitution and the income effect of this price change. So we're going to decompose these effects into 2 parts. So the way to do this is to recall what the substitution effect measures. So the substitution effect tells us how will the consumer change their consumption in order to keep their utility the same, but facing new prices. Okay, so this is a very, very loose way of describing what it is. Essentially, if we have to think about the graph, this represents staying on the same indifference curve that you are on, but because you now face new prices, it means that you have to find where your marginal rate of substitution is equal to the new relative price. So you initially were maximizing your utility by equating your MRS, and your MRS is your marginal utility ratio, by equating your MRS with the relative price. If one of those prices change, then it means that your MRS will no longer be equal to the relative price where you are currently consuming, which means you then have to change your consumption in order to make your MRS and relative price equal again, but with the goal of remaining on your original indifference curve. Okay, so what that implies is that we want her utility to remain at 50. Okay, so that is what we want to achieve. So 50 must be equal to x times y. So she must consume some combination of x and y that gives a total utility of 50. And that x and y must be such that the MUX over MUY is equal to the new price of x, which is 5, divided by the new price of y. Sorry, not the new price. The price of y stayed the same, which is 2. Okay, so we know that MUX is y and MUY is x. So we have this. Y over x must be equal to 2.5. So y must be equal to 2.5x. Okay. So what I can then do is I can substitute this into that equation there. I can say that 50 must be equal to x times 2.5x. So 50 must be equal to 2.5x squared. And now I can solve for the value of x when we make that substitution, when we move along the indifference curve, trying to maintain the same level of utility. So how I would need to do this is I would divide both sides by 2.5. So I'd get 20 is equal to x squared, which means I then have to take the square root of 20 in order to find the value of x at the end of that substitution effect. So the square root of 20 is going to be 4.47. Okay. The value of y is then going to be 2.5 times that 4.47. So that's going to be 11.18. So these two values tell me that originally her consumption of x was 4 and her consumption of y was 10. And so the substitution effect on x is plus 0.47. And the substitution effect on, sorry, was x5. I was going to say that didn't make sense. So the substitution effect is from 5 to 4.47. So it's minus 0.53. And the substitution effect on y is plus 1.18. Okay, now the reason why I could immediately identify that that positive there was wrong is because something that is really important about the substitution effects is that they will always be in the opposite direction. So because the price of x went up, it means that x is now relatively less attractive than y. If the price of x goes up, it means whatever additional utility the consumer can get from x, from what they spend on x, is now less. So it is more expensive satisfaction, to put it in those terms. Whereas the marginal utility that you get from Y in relative terms is now going to be greater. So the substitution effect should be negative for X and positive for Y, because a rational consumer would substitute away from X towards Y. So if this, let's call A her original consumption bundle, that was 5X and 10Y, the substitution effect then takes her to a new bundle, I'll call it B, and that bundle is 4.47 and 11.18. The income effect then takes us all the way to the final consumption point. So the total effect, if we add the substitution effect and the income effect, we have that full total effect of the price change. And we already calculated that to be 410. So that tells me that the income effect for X or on X is going to be minus 0.47 because it's going from 4.47 to 4. And the income effect for Y is going to be minus 1.18. So going from 11.18 to 10. So that's why we end up with the same amount of Y in the original best affordable points and the new best affordable points, is because the income effect and the substitution effect perfectly erase each other. They're perfectly balanced. So they're perfectly counted. The substitution effect, which was plus 1.18, is now counted by a negative substitution effect of minus 1.18. Okay, so these are the substitution effect and the income effect for X. Now, given these income effects and given the price change, what type of products are X and Y? So what we have in this example is we have the price of X going up. If the price of X goes up, the consumer's purchasing power falls. So this individual has fewer consumption possibilities after the price increase in X. The fact that their purchasing power is less and the income effects are negative for both products, X and Y, tells me that these two goods are both normal goods. In a response to a lower purchasing power, this consumer consumes less of both goods. So that's how we can extract whether or not this product is normal or inferior by observing the direction of the income effect. Does that make sense? So quite a lot of context, but a lot of theory that I've covered in one question. Okay, so I see a question in the chat that says, are we going to get questions of the same difficulty level? Or are they going to be harder? My questions are going to be of the same standard that they were in the tutorials and in the A1. Whether or not you think that was hard or not, I mean, that's down to you. I set questions that make use of the theory. I don't like to talk about questions as hard or easy. It really depends on the student who is writing the test. Like I said, it's your knowledge, not the questions. Why do we do why the subject? So it's all coming back to me now. That sounds like an 80s song, or at least a lyric from an 80s song. Miss Mbata, so why do we do why the subject? I'm just trying to... Do you mean why did I choose why as the subject here? Or just in general? I mean, the reason why I chose y to be the subject here is because if I'd made x the subject, I would have had y over 5 plus a fifth. It's just more awkward to work with fractions. So I find it a lot easier to work with whole numbers than with fractions. So that's the reason why I chose y to be the subject there. No other reason than what would be algebraically easier. Question, if both x and y's income effects were positive or increased, would there be inferior goods? Absolutely. Exactly. So if one product has become more expensive and both income effects are positive, it means they would both be inferior. Now, the way that the problem is set up and the way that the math works, you would never get an example of two inferior goods. You would only ever get an example with two normal goods or one normal good and one inferior good. The math wouldn't solve if you had two inferior goods. So you won't get that kind of example. What should have happened here to classify these as Giffen goods? Okay, that's a great question. So a Giffen good is classified by the income effect exceeding the substitution effect. Okay, so a Giffen good is an inferior good. So we have to interpret the income effect and substitution effect in relation to that, but it's an inferior good whose income effect is larger than the substitution effect. And the reason why this gives us a Giffen good is because let's say there's been a price increase for this particular good. It means the income effect would be positive and the substitution effect would be negative, right? Because if the thing becomes more expensive, we substitute away from it towards the other good. And if the price goes up, my purchasing power goes down. And because it's an inferior good, my income effect is positive. If the positive income effect exceeds the negative substitution effect, the overall total effect will be positive, which tells me that prices going up makes quantity demanded go up. And that contradicts the law of demand. The law of demand says if price goes up, quantity goes down. So Giffen goods have upward sloping demand curves. If prices go up, we consume more of it. Okay. And the reason this happens is because it's an inferior good whose income effect dominates the substitution effect. Really great question. Okay, everyone happy with this question? Can I move on to the next one? Cool. Okay, so the next question, let me quickly open my question set again. Okay, so the next question comes from tutorial 4, question 4. So it is an elasticity question. And it's specifically a cross-price elasticity question. I'll also show you the elasticity question from the A1 as well, because the formulas are pretty much the same. It's just the interpretation that changes. So for tutorial 4, question 4, we get told that the demand for product X is linearly determined by the price of a related product Y. In other words, X and Y are related in some way. Either they are substitutes for each other or they are complements for each other. Then we get told in 2023, the price of X was $3 and the quantity sold of X was 400. The price of Y was $10 and the quantity sold of Y was 200. In 2024, X still cost $3, but only 300 units were sold. Y cost $12 and 150 units were sold. Okay, the question then asks for the cross-price elasticity of demand for X with respect to Y in 2023. Now, we could actually calculate a few elasticities with the information in this question. So I'm first going to calculate the cross-price elasticity, but then we can also calculate the price elasticity of demand of X and the price elasticity of demand of Y. Those are also possible with the information given here. Okay, so the cross-price elasticity of X and Y, we calculate as how does the quantity of X respond to a change in the price of Y. So an elasticity formula always has a percentage change in the numerator and the denominator. The type of elasticity we're working with will tell us what these numerator and denominator variables are. So when we're looking at cross-price elasticity, we want to see how do people's decision to purchase X, how does that decision respond to a change in the price of Y? I can rewrite the percentage change in the quantity of X as the change in the quantity of X divided by the original quantity of X, which is the quantity in 2023. And I can also represent the percentage change in the price of Y as the change in the price of Y over the original 2023 price of Y. If I now replace that division sign with a multiply, that means swapping those two around. So I can then re-represent my elasticity as the percentage change in X over the quantity of X times the price Y over the change in price Y. And then I can do something else. I can say then that the change in the quantity of X over the change in the price of Y is equal to price Y over QX. So this is just another way in which we could represent the elasticity formula. This becomes most useful when we do price elasticity of demand, which is why I'm showing it to you. But what we're going to do now is we're going to sub in values from up here into this formula. Okay, so what was the change in the quantity of X? The change was from 400 to 300. So the change in the quantity of X is minus 100. What is the change in the price of Y? It was from 10 to 12. So it is plus 2. So that's the change in the quantity of X. That's the change in the price of Y. And then the original price of Y was 10. And the original price of X, quantity of X was 400. So here I have my values subbed into my formula. So what I'm going to end up with is a cross-price elasticity value of minus 1,000 divided by 800, which is minus 1.25. Okay, now when it comes to cross-price elasticity, the sign is the thing that we interpret. So this negative tells us that when the price of Y went up, people responded by reducing their consumption of X. That tells me that these two products are complements. Complements are things you use together, okay? So if the price of Y goes up, we would buy less Y, and we can see that in the data. The price of Y went up, the consumption of Y went down. Now, because we are using less Y, we will then, as a result, use less X if it is a complement. So a negative cross-price elasticity tells me the two goods are complements. If you get a cross-price elasticity that is positive, then it tells you that the two goods are substitutes. Because if the price of a product goes up and consumers respond by buying more of something else, it must mean that you are choosing to replace the thing that is now more expensive with the other product. So it has to be a substitute for the now more expensive product. So a positive cross-price elasticity would then indicate substitutes. Okay. What I'm now going to do is I'm going to show you how we can also have calculated the price elasticity for, let's say, product X using this information here. So I could have also said, what is the price elasticity demand of X? And we would use the same formula, except now instead of comparing the percentage change in the quantity of X to the percentage change in the price of Y, we would be comparing the percentage change in the quantity of X to the percentage change in the price of X. So we use the same formula. We have change in QX over change in price X times price X over QX. So it's an identical formula because this formula at the end of the day just measures responsiveness of one variable to another. So it's just about which variables end up in this equation. And here we're wanting to show how quantity of X responds to the price of that same product X. Okay, so the change in X is 400, 300. Oh yeah, there's actually going to be a zero elasticity here because I've chosen the wrong product to use because the price of X didn't change. So that's a bit of a redundant question. So I'm going to make this Y instead. Yeah. Okay, so I'm going to make it the price elasticity of demand of Y. So the change in the quantity of Y is minus 50 from 200 to 150. The change in the price of Y is 2 from 10 to 12. The original price of Y is 10 and the original quantity of Y is 200. So now I have minus 500 divided by 400, and I get minus 1.25. So effectively, I'm getting the same answer as I did for cross-price elasticity, but that is simply a coincidence, okay? Pure coincidence. It's just the construction of the values in this question. When we interpret price elasticity of demand for a single product, so we're not looking at cross-price elasticity, we interpret the absolute size of that elasticity. So in effect, we ignore the sign. And the reason we ignore the sign is because the law of demand would tell us that most of the time, okay, given goods are a contradiction to this. Most of the time, if the price of something goes up, the quantity of that good that is bought and sold goes down. So we know that it will be negative. It's kind of a given. What we want to judge then is the magnitude of the relationship. So we see that in absolute terms, the elasticity is 1.25. So it's greater than 1. And if we have a price elasticity of demand value that is greater than 1, it tells us that this product has price elastic demand. Okay, so when the price of this product changes, the response by consumers in terms of how much less they buy because the price is going up will be proportionately larger. So the percentage change in quantity as a sort of percentage change as a proportion is greater than the percentage change in the price. Okay. Everybody happy with elasticities? It is one formula. The trick is knowing what to put in the formula and then how to interpret the answer in relation to the problem at hand. Are we looking for income elasticity, cross-price elasticity, or price elasticity of demand? Okay, so that is elasticity. I just want to quickly check the past. So A1's question that looked at elasticity, I did give a very detailed memo for this, so I don't think I'm going to go through it because there is a memo. The only other additional thing that we can ask around price elasticity of demand, aside from interpreting the nature of the elasticity, so whether it's inelastic or elastic, is to ask you about total revenue. So the important theory here is that if a vendor or if a supplier, a seller, is wanting to strategize around price and they want to choose a price change that is going to be good for their total revenue, so increase their total revenue, they need to be aware of the elasticity of their product. If their product is price inelastic in demand, it means that they can increase their total revenue by increasing their price. So an inelastic demand, so if demand is price inelastic, it means that raising the price will lead to a higher total revenue. If it's price elastic demand, then lowering the price would result in higher total revenue. So in tutorial 4, of I think it was 4, or was it 5? One of the last 2 tutorials, there is a question about raising the price of public transport. So public transport will, more often than not, have price inelastic demand. And so one way in which revenues can be increased in public transports is to raise the fare. But then something that we discussed in the slides is, but what about the equity issues of raising the price of something that is a necessity and also is a service that is predominantly used by people who are of the working class or people who are living further away from work, people who maybe earn lower wages, etc. So that's another way that we thought about elasticity during the semester. Can ma'am give an example of a Giffen good? The only example in history of a Giffen good is potatoes during the Irish famine. But there is a whole nother argument for why that was. But that's the only example that I have seen in the world. It is a very, very rare case. So yeah, not easy to find examples of it. Okay, now let's go to the next question. Just going to check which tutorial question, what was the next tutorial question I chose? Okay, so the next tutorial question was from tutorial 5, question 3. Okay, so this is the new work that wasn't covered in the A1. So this is to do with intertemporal decision-making, but also how it is that somebody can be better off or worse off when both prices and incomes change. So I'm going to go through an example like that now. So this is question 3 from TUT 5. So the question says, Jordan spends all her annual income on 2 goods, X and Y. The price of X is 15 and the price of Y is 25. In 2025, she consumed 2,000 units of X and she consumed 3,000 units of Y. The first question then asks, what was her annual income in 2025? Okay, so what we need to know here is that she chose to consume this combination, facing these prices and having some income that she could then divide between these 2 goods. So that tells me that this combination is her best affordable consumption point, that is her best affordable bundle. And a best affordable bundle is one that uses up all income. And so if I calculate what this combination cost her, I would have her income. So her income is going to be 2,000x times the price of X, which is 15, plus 3,000Y times the price of Y, which is 25. So that gives me 2,015 is 330,000 plus 3,000 times 25. So that is 105,000. Okay, so that was her income in 2025. That is the income that would have been spent in total on this combination of X and Y. We then get told that in 2026, the price of X is now 6. So X has become a lot cheaper. The price of Y is now 30. So Y has become more expensive. And her income is now 102,000. So between 2005 and 2006, Y has become more expensive, X has become cheaper, and her income has gone down. We want to know now, can she still afford her preferred bundle from 2025? Is 2,000X and 3,000Y a possible consumption choice for her? So what we would need to do is we would need to find what does 2,000X, which now costs 6, plus 3,000Y, which is now 30, add up to in total spending. It would be 12,000 plus 90,000, which is 102,000, which is exactly her income. So this tells me that even though Y has become more expensive, X has become cheaper, she is still able to afford her chosen bundle of 2025. And that is important because it means she can't be worse off than she was. It is impossible for her to be worse off. As long as she can still choose the same bundle this year as she could last year, it means she can be as satisfied this year as she was last year. She can get the same utility this year as she did in the past. So she can't be worse off. So if you get a question in the A2 where you get values like this, and the question says, is this person worse or better off? As long as you can prove that they can still afford their original best affordable bundle, given the new prices and income, as long as they can still afford that, they can't be worse off. Okay. What we now want to figure out is, can she be better off? So we know she can't be worse off, but can she be better off? So we're going to draw her two budget constraints, and we're going to show her original best affordable points on this picture. And that will reveal to us whether or not she can be better off in 2026. So on the x-axis, we have her consumption of X. On the y-axis, her consumption of Y. Her original budget constraints. So her income was 105. And the price of X was 15, and the price of Y was 25, which means in 2025, if she spent all 105,000 on Y, which costs 25, she would have been able to consume 4,200 units of Y. So that is the Y-intercept. It represents her real income in terms of Y in 2025. If she had instead spent all her 105,000 on X, she would have had 7,000 units of X. So these 2 points represent her real income in terms of X and Y in 2025. And if I combine or join these 2 points, I end up with her 2025 budget constraint. And I'm going to label it B1. Okay, so how does her 2026 budget constraint look? So now her income is 102,000. The price of X is 6 and the price of Y is 30. So if she spent all her income on Y, she would get 3,400 units of Y. So that's 102,000 divided by 30. If she consumed with all of her income on X, she would get 17,000 units of X. Okay, so I'm not drawing this to scale, but it brings home the point. If I then connect those 2 points, I find my 2026 budget constraint. What we already showed is that she had exactly the right amount of income in 2026 to consume 2,000 X and 3,000 Y, which means that the only points on these 2 budget constraints that are shared is that bundle 2,000, 3,000. Okay, we've already proven that 2,000, 3,000 lies on both B1 and B2. So this is her best affordable bundle in 2025. Okay, now if I was going to draw an indifference curve that is tangent to that A and the B1, so tangent to the B1 at that bundle A, that indifference curve would look something like this. Okay, so A is the best affordable bundle in 2025. It is the point of tangency between her budget constraint B1 and a highest attainable indifference curve I1. Now, why this is important to illustrate is because what we can then see is that if she had to move along this indifference curve, so this is the level of satisfaction she was able to achieve last year. If we move along this indifference curve, we remain equally satisfied. So if she had to be at a point like this, which she can now consume because all of these bundles here, they represent new possibilities for her. They represent feasible options. These are bundles that weren't affordable with B1, but are now affordable with B2. So this point here, she can stay as happy as she was last year, and she can afford it. But then we notice that this bundle lies inside her new budget constraints. And so in actual fact, she could be more satisfied. She now has the ability to consume on the higher indifference curve that is now tangent to her new budget constraints. So this visual proves to us that she can be better off. Okay. So by drawing the picture, we can then see that Jordan will be better off in 2026 than she was in 2025 because she can reach this higher indifference curve. Does that make sense? Okay. Mr. Welsh, I thank you so much for, and who's it? Oh, yeah, Miss Phillips. The two of you always gives me thumbs up. So I'm using you as my guides of whether or not to move forward with the next question. So thank you very much for always putting your thumbs up. Okay, I'm going to now move on to an intertemporal budget constraints question. Okay, so the final question in tutorial 5 told you that Soreka earns $55,000 in the current period. So this is her M1. So time period 1, she gets $55,000. In time period 2, so in the future period, she gets $60,000. So for the intertemporal decision-making problem, we only consider 2 time periods. And the reason why is because then we can represent a 2-dimensional picture. It just becomes a lot easier to solve mathematically. So 4.1, so the first part of this question, this is TUT 5, question 4. The first part of the question asks, what is the maximum interest rate that would allow her to spend $105,000 in the current period? So what this question is asking is, if she was to borrow against her $60,000 future earnings, what interest rate would allow her to turn that $60,000 of the future into $50,000 today? Okay. So why do you think I'm saying $50,000 today? It's because she has $55,000 now. She wants to consume $105,000 right now, which means she needs an extra $50 to bring her 55,000 up to 105,000. That $50,000 will be her $60,000 of the future, discounted by some maximum interest rates. So what we're calculating is $105,000 is equal to current 55 current income plus future income discounted by some interest rates. So we're dividing 60,000 by 1 plus R. And R is what we are trying to solve for. So if I take the 55,000 to this side, I get 50,000. So 50,000 is 60,000 over 1 plus R. So I then take the 1 plus R to this side. So I get 50,000 plus 50,000 times R equals 60,000. I then deduct 50,000 from both sides. So I get 50,000 R is equal to 10,000. And now I divide both sides by 50,000. So I get R is equal to 10,000 divided by 50,000, which is 0.2. So the maximum interest rate that would allow her to spend 105,000 in the current period is 20%. Okay. So this is how we would work out the present value of lifetime income. So her lifetime income is made up of her income this period and the income in the future. But if she wanted to bring all of that into the present, we would have to discount her future income by the interest rates. So this is the maximum interest rate allowing her to spend $105,000 in the current period. The next question then says, what minimum interest rates would allow her to spend $120,500 in the future? So how can she consume $120,500 in the future? Well, this means that she would have to save her current income in order to bring her future income to $120,500. So what we would calculate here is $120,500 is equal to her current income multiplied by 1 plus R. So she puts this in the bank and earns interest on it. And then she will also have her future income of 60,000. So here I would take 60,000 to this side, and I then get 60,500 equals 55,000 plus 55,000 R. If I then take 55,000 away from both sides, I get 5,500 is equal to 55,000 R. And then I divide both sides by 55,000. And so that's going to give me 0.1. So the minimum interest rate that would allow her to have a future consumption of $120,500 would be 10%. Does that make sense? Okay, cool. I see Sophia, you asked, is there a way to answer this question mathematically instead of graphically? I'm guessing you mean the previous question. So the question with the change in prices and income. It wouldn't be possible to do this mathematically without having the utility function. So we don't know what the utility function is, but we can reasonably assume that this consumer has well-behaved, usual-looking preferences. So this person has convex indifference curves. And so that's why I can plot it like this and then reason that this person would be better off in the future. So for this type of question, without knowing what the utility function is, it would be best to just draw it and then see that indeed it offers her more possibilities, which then means she can end up on a higher indifference curve. Okay, so yeah, that it would require some additional functions for you to do it mathematically. Okay, so that was to get the interest rates. To then move on to the next part of the question, which says, suppose the interest rate is 15%. So let's suppose that R is 0.15. How much would she be able to spend in the future period if she chooses to save $25,000 of her current income? So we want to know what is her consumption in the future going to be? So what will C2 be if she saves $25,000 and that $25,000 earns interest of 15%? And then we would add her 60,000 of future income because that is also available to her in the future to consume with. So 25,000 times 1.15 is going to be 28,750. And if I add that to her future income, it means she will be able to consume $88,750 worth in the future. Okay. 4.4 then asks, what is the function of her intertemporal budget constraint given the interest rates of 15%? Okay, so the intertemporal budget constraint works exactly the same way as any sort of budget constraint that we've worked with. So in most of the work we covered, we used contemporaneous, so atemporal budget constraints. So we only looked at the consumption of two goods at a particular point in time. But when we consider intertemporal decisions, what we're then modeling is consumption today and consumption in the future, and what combinations of current and future consumption are possible given the incomes of today and the future and the cost of future consumption. So the interest rates in the intertemporal decision-making model represents the cost of consumption where you are borrowing against your future self. So it's the cost of choosing to consume more today rather than consuming more in the future. And that kind of makes sense because we think about any budget constraint, we say that the slope is the relative price of the good on the y-axis, right? So the negative of the relative price. So the slope of our budget constraints is going to be R, which then represents the relative price of current consumption. So it's what current, well, actually it's going to be 1 point, not R, it's going to be 1 point R. So 1 plus 0.1 if it's 10%, or 0.2 if it's 20%. So it's going to be the cost of current consumption. So how we would find our intertemporal budget constraints is we would say that this intercept represents the maximum amount that we would be able to consume in the future if we consumed absolutely nothing today. So if we put everything into the bank and just saved towards maximizing our future consumption, that would give us that y-intercept over there. So our y-intercept is going to be M1 times 1 plus R plus M2. So this represents us putting all of our income from period 1 into the bank, and this is our future income. So this is the y-intercept of our intertemporal budget constraints. So this is M1, 1 plus R plus M2. The same logic would then tell us that this intercept here would be how much could we at maximum consume today if we choose to consume nothing in the future. And so that would be M1 plus M2 over 1 plus R. So this is the present value of our lifetime income. That's what gives us the x-axis intercept. And if we combine those two or join those two intercepts with a straight line, this is our intertemporal budget constraints. Okay, so those are the two intercepts. The function of this line would then be C2, so that's y, is equal to the intercept, which is M1, 1 plus R plus M2. So that's the y-intercept, minus, because it has a negative slope. And then the slope of this line would then be representing, if I chose to consume 1 extra rand today, how much would that cost me relative to 1 rand of consumption in the future? So it basically has to represent what is the relative cost of current consumption. And so the relative cost of current consumption is 1 plus R. If I want to consume 1 extra dollar today, it's going to cost me 1 plus R to do so. I'm going to have to pay interest for the ability to do that. And then that's going to be multiplied by C1. So this is the same as y equals C plus mx. So that's just a linear function. Okay, but the same logic applies here as it applies to any linear budget line. This is the maximum amount of y. So what is the value of y? The vertical variable, in this case C2, when x, the horizontal variable, is 0, minus the relative price of the good on the x-axis. In this case, it's current consumption. So it's going to cost you 1 plus R dollars or rands for each 1 rand extra to consume today, and then multiplied by the x variable, which is C1. So it looks confusing, but if you break it down into those economic concepts, then it's pretty simple to derive for yourself. Okay, So the intertemporal budget constraint looks like this. And then just like any atemporal consumption decision, we look for where this budget constraint is tangent to some highest attainable indifference curve. And this indifference curve, we call the slope the marginal rates of time preference, MRTP. So it indicates how patient or impatient this consumer is, how desperate they are to consume right now versus how patient they are to wait for future consumption.